So let's get started. So what we see out there in the literature and also in huge tech is that we see increasingly speech models out there, and they have more and more capabilities. And the thing that they mostly promise is somewhat universal speech processing. But when we actually zoom in on some applications, for example, automatic speech recognition, we see that there is huge variability, for example, in the performance between languages. So on this slide, you see a figure from the Whisper paper where it's shown that the different languages exhibit very much different word error rates. And although there is a correlation with the amount of data that's available, some languages basically do not have the prospect of obtaining more. And I think it's interesting because also the paper quoted and mentioning that Whisper speech recognition performance is still quite poor on many languages. And this is, of course, an example from a single model, but this holds for other models too. So another example on this slide is from the paper presenting the MMS model. And I just got a small excerpt from a larger figure showing some languages with different models, so different versions of the MMS models they released, comparing it also to Whisper, showing basically the same thing. So different languages have a very large variability in terms of performance. And this is, of course, problematic. And addressing this challenge could really help improve the digital participation of many speakers worldwide. Because it's well known that a well-performing ASR system can help provide speakers access to valuable information and services. So in this talk, I will talk about our work and actually argue that we need two things to address this challenge as well as possible. So the first thing is that we actually need better ways to reliably measure speech recognition model performance. And I will talk about more about the motivation and details in the first part of the talk. Then in the second part of the talk, I will argue and explain new algorithms that we need and that a new algorithm that we developed to bridge the performance gap between languages. So yeah, it's a twofold part. So first, better ways to reliably measure speech recognition model performance, and then new algorithms. So for the first part, I want to talk about our recent paper where we present ML Superb 2.0, which is a new benchmark for benchmarking multilingual speech models across modeling constraints, languages, and data sets. So I would like to start with some background on ML Superb. So these recent multilingual speech processing models, from which I highlighted two examples in the beginning of the talk, they have the capacity nowadays to model hundreds of languages. However, if you closely look at the evaluation setups, they are often compared and evaluated using different experimental configurations. And this limits the extent to which they can be reliably compared. And this was basically the motivation also to develop a multilingual speech processing benchmark to basically mitigate this limitation. So ML Superb is not the only one out there. There are actually great efforts in the community on spoken multilingual benchmarks, and I highlighted some examples on this slide. And the thing I wanted to highlight in the comparison is that ML Superb is actually the most comprehensive one in terms of language coverage. So as the name indicates, ML Superb 2.0 actually builds upon the first version of the benchmark, ML Superb, which covered 143 languages and evaluated models on monolingual and multilingual ASR, language identification, and a joint prediction task of multilingual speech recognition and language identification. However, there were some limitations with the design of ML Superb. So the first one is that it's strictly considered a fixed benchmark setting where we froze the layers of self-supervised models and then trained a shallow downstream model on top of the models, which we use to predict transcriptions in a language identification label. And while this is efficient, it is not generalizable enough to various settings. And there's also a whole bunch of literature on showing that when you change the, let's say, downstream model on top, the performance of the models or the rankings might actually differ. So one could argue that it also not takes really application requirements or users budgets into account because it was not flexible. So this limitation motivated us to develop a new version of the benchmark where we had more flexible constraints. The second limitation I wanted to discuss is that the original evaluation metrics do not really provide insights into performance variation between individual languages and data sets. So it computed an aggregate score, basically, from which it was very difficult to reason about these variations. And this motivated us to change the way we evaluate it to place greater focus on robustness across languages and data sets. So what does ML Superb 2.0 actually look like? So these limitations combined, we create a new version of the benchmark that relaxes the fixed constraints and improves the fairness in evaluation metrics so we can actually evaluate robustness across languages and variation across data sets. In ML Superb 2, we basically focus on one single task, which is the joint multilingual language identification / ASR task, and applying ML Superb 1, as there were some labeling errors identified in some data sets. So to briefly summarize the data we use to train and evaluate models is that we have data from 141 languages, which are sourced across 15 different data sets. And this means we had approximately 300 hours in total, meaning that we take 1 hour of data from each language dataset pair, but some languages occur in more than one dataset, so hence we have 300 hours in total. And in addition to this 1 hour that we use for training, we have both 10 minutes for validation and 10 minutes for test data from each language dataset pair. 20 languages from the 141 are reserved for few-shot learning experiments, where we basically randomly sampled 5 utterances and used those for training. Some details about the experimental setup is we used the ESPNet toolkit to train the models and loaded the front-end models using this S3PRL toolkit. And the two models, self-supervised models we evaluate on the benchmark are XLSR and MMS. And these were chosen because they had the best performance on the original benchmark. So to keep the overall setup of the benchmark also relatively lightweight, we kept the number of tunable parameters to 100 million. And this was basically in line with practices of the original benchmark as well. So I talked about the need for more flexible constraints. And what do these flexible constraints actually look like? So specifically, we investigate 4 new benchmark configurations. So instead of taking a self-supervised model, freezing the representations, and training a shallow model on top, we now have 4 different configurations with several different models that I will talk about. So the first one is that we use larger scale downstream models. We also consider model fine-tuning approaches. We look at efficient model adaptation strategies. And in addition to self-supervised models only, we include Whisper and OWSM, or Awesome, the open source variant of Whisper, which are supervised pre-trained models. So the composition of the benchmark, given the larger downstream models, actually looks like the following. So we take the self-supervised models, like XLSR or MMS. We freeze the intermediate layers. We then compute a weighted sum of these layers, which we use as input to a downstream model. And we consider two different frameworks here. So a CTC only framework and a CTC attention-based framework. So let's look at the CTC framework first. So we use the weighted sum as input to models of three different architectures. So these are like three separate models. So one is a E-branch former encoder, we consider a conformer encoder, and we consider a transformer encoder to see if like the different architectures have any effect on downstream performance. The CTC framework has like a linear output layer to map the model outputs to a language ID label and a transcript. Actually, for the CTC attention-based framework, it's kind of similar, but the composition of the models is slightly different. So instead of having an encoder only, the CTC attention-based framework considers encoder, decoder, downstream models. So we have, again, the branch former, conformer, and transformer, but each of them are also combined with a 8-layer transformer decoder. Moving on to the model fine-tuning configuration of the benchmark, we have a slightly different approach where we, again, take the pre-trained model, freeze the representations, but for some layers, we actually do update model parameters. So we either fine-tune the bottom layers, we fine-tune the middle layers, or we fine-tune the top layers, do the weighted sum again, and use it as input to either the CTC framework and the CTC attention-based framework, where this time it's a 2-layer encoder and a 2-layer encoder plus a 4-layer decoder. In addition to these partial fine-tuning strategies, we also perform full fine-tuning, which of course updates more than 100 million parameters, but basically we do this for reasons of comparison. The third configuration was efficient model adaptation strategies, which is kind of similar to the partial fine-tuning method described on the previous slide. But instead of fine-tuning like some parts of the model, we insert parameters into the model using commonly known adaptation strategies such as adapters and LoRa, and we basically employ the same approach. So we update the LoRa and adapter parameters and use it as input to the same frameworks and downstream models as shown on the previous slide. For the supervised models, we had a slightly different approach. So as mentioned before, we consider Whisper and Awesome, which is the open source variant of Whisper that was trained in Shinji Watanabe's lab at CMU. So what we do within the CTC framework, we basically evaluate the capabilities of the encoder part of these models, from which we also fine-tune the top layers of the encoder and use it as input to this downstream model that we now know. And in addition to evaluating the encoder only, we also look at both the encoder and decoder. And in this case, we only fine-tune the top layers of the decoder using the original training loss of these models because they already have their own decoder. Cool. So that's basically what the configurations look like. So to actually train models, we follow hyperparameters basically discussed in prior work. More details about that can be found in the paper. And we tune the learning rate and select the best performing model on the validation set I previously mentioned. So how do we evaluate models? So after training, we compute an accuracy score for the language identification task, and we use the character error rate for the multilingual speech processing task on the two sets. So we had the 121 languages in the normal setting, and we had 20 languages in the few shot setting. So to place some more focus on measuring robustness, we compute the macro average over languages and data sets instead of just a single micro averaged character error rate. So what we do is we basically compute the macro average of character error rates across all data sets per language, if there is more than one data set for a language, and then compute the macro average of those character error rates as the per language character error rate. In the end, we still report a single character error rate, which is basically then again the average of the per language character error rates. And this way of computing scores actually allows us to better understand performance differences between data sets, but also between languages. And the way we try to highlight that in the paper is like adding some descriptive statistics, so at least compute a standard deviation across the language-specific character error rates and measure the character error rate range between data sets in the same language. In addition to that, we were inspired by work on fairness in machine learning. So we also added the character error rate of the worst performing language to see basically the discrepancy between the worst performing one and the average score. So let's move on to actually look at some results from the benchmark. I would like to talk about this in the following order. So first, look at the effect of introducing the 4 benchmark configurations, then see how actually model ranking is different for the different configurations. Talk about supervised models versus the self-supervised models, and then talk about variation across languages and data sets. So on this slide, I summarized the best performing configuration from each of the 4 configurations that we introduced in ML Superb 2.0. So this table shows in red the best performing model and configuration on the original ML Superb benchmark, so the first version, where MMS plus the CTC framework with the transformer architecture showed the best performance. So the average character error rate was 24.7 with a standard deviation across languages of 12.3. And the language identification accuracy was over 90%. So what we see with the new configuration, so the larger downstream models, model fine-tuning, model adaptation, and the supervised models, is that all of these on average improve over the configuration of the original benchmark. So one could argue that ML Superb is actually a better estimate of model performance compared to the original ML Superb that left like a substantial amount of performance still on the table. So one could look at ML Superb 2.0 basically as a better device or better microscope to zoom in on the performance of the true performance of the models evaluated. However, the interesting thing is that when we consider different training settings, the ranking of the upstream models can actually be different. And this is also known in the literature, but still worth it, I think, to look at in more detail. So if we look at the model ranking given the different configurations on this slide, I basically try to summarize the best performing model given the larger downstream model configuration. So here we have the transformer, conformer, branchformer architectures within both frameworks. And you can see that although MMS is the best performing model in the majority of the configurations, XLSR performs better in 2 of them. If we then move on to the model fine-tuning approach, we see actually a different ranking again. So in this case, MMS is clearly the better model. as XLSR doesn't outperform MMS in any of the evaluated cases. If we then look at the efficient model adaptation approaches, we see that the ranking again is different. So here with LoRa and adapters, XLSR is the better model in the CTC framework, and MMS only outperforms XLSR when we evaluate the encoder-decoder setup in the attention-based CTC framework. So that's about like model rankings for the self-supervised models. So now I want to briefly highlight also the inclusion of supervised models, as the original benchmark only focused on self-supervised pre-trained models. So the only disclaimer we of course have to make is that we need to assume that the ML superb data was like not used, for example, for whisper training, as we cannot know that for sure. So this is basically some first steps in the direction of adding supervised models here. So let's look at this table now. So here we have the same downstream model to enable a fair comparison between the different models evaluated. And we see in this case that, so with the transformer encoder and the CTC framework, that the self-supervised models actually tend to perform slightly better than the supervised models. Moving on to the variation across languages and data sets, we see that in each of the evaluated settings, so for example, it's also visible on this slide, that the standard deviation across languages is very large. And this applies to both the normal settings that I discussed in the previous slides, as well as the few-shot settings that we report in the paper. So this actually shows that there is a lot of variation among the language-specific character error rates. And the impact of large differences is also highlighted by the character error rate of the worst performing languages. So in most cases, so in most configurations, the character error rate of the worst performing language exceeded 50 or sometimes even 60%, for example, for languages as Lao or Minnan Chinese. This observation of large differences between languages also translates to the different data sets, where we saw large differences between data sets in the same language, highlighting the impact of domain or acoustic differences. So this is basically a lot of information, and I will try to summarize some conclusions and takeaways from this benchmark. So ML Superb is an updated version of the original ML Superb benchmark, which has more flexible constraints. So we investigated 4 different configurations that ML Superb didn't consider before. And we also introduced a broader set of evaluation metrics to at least shed some light on variation across languages and data sets. So we've seen that all new configurations actually show improvements over the configurations used in the original ML Superb dataset benchmark, which was basically likely underestimating model performance, as a lot of performance was left on the table. The interesting thing is that the model ranking actually depends a lot on the configuration of the benchmark. So we saw that each of the different configurations actually led to different rankings of the individual models. So it seems there is really no single way to evaluate a self-supervised model, as it must always be measured within the context of a specific downstream model and task to enable a fair comparison between models. With the introduction of the more elaborate evaluation metrics, we really also encourage research on methods that can help improve the robustness across language and data sets variation. So hopefully this benchmark can be like a stepping stone to achieve this goal. So this is the end of the first part. So if there are already any clarification questions, please feel free to ask some, and otherwise I will move on with the second part of the talk. If I don't hear anything, I will probably just move on.
Maybe I could ask one question.
Yes.
On slide 24, you talk about different layer you choose for fine tuning. So what is the strategy? How do you decide which layer to use? For all the models, you use all different combination of layers to fine tune, or is there any
Yes.
specific strategy?
Yeah, thank you for asking this question. So it's basically, this can be seen as like different models that we fine tune. So we either only fine tune the bottom layers of the model, then we evaluate fine tuning the middle layers separately, and then again separately, we train a model where we only fine tune the top layers. And because we need to cap performance at cap like training at updating 100 million parameters, we basically try to see, okay, which of the parts of the models contain like different kinds of information. So we target the bottom versus the middle versus the top.
I see, I see. And when you apply the LoRa or something, it is the same strategy. You append, for example, the adapters to the different layers, or it is only one strategy for that?
Yes, here is it just a classic standard approach. So adapters are inserted, I think, in every transformer layer, for example, of the models. So this is like just a standard way of using adapters and LoRa. Nothing fancy going on.
Yeah.
Okay, let's move on. Cool. So given that we see these large differences in performance between languages, we really asked ourselves the question, can we ourselves do a better job? Can we develop more robust optimization methods that can basically address the performance gap that we observed? So the first thing I wanted to highlight is trained. And the standard approach is here empirical risk minimalization, basically minimizing the average training loss on the training data. And what happens in a like schematic overview is that this works very well on average, but it doesn't exclude that the models perform much worse on some distribution of your training data. And this behavior has been observed in many different applications, ranging from speech recognition, where papers have shown that models perform very different on speech from white versus black speakers, for example. It has been shown in language identification or in image classification. So this is really a much broader machine learning problem. And ideally, what we want to achieve is that the models perform good on average, but that the performance of this worst performing group, let's say, also is comparable or hopefully as good as the performance on average. And to achieve this goal, we were inspired by work on distributionally robust neural networks for group shifts, work that has been done a couple of years ago here at Stanford, where basically they showed that instead of minimizing the average training loss on the training data, one could minimize the worst case expected loss over a set of predefined groups in the training data. And this group DRO paper showed very strong performance on image and text classification tasks, where models use, for example, a cross entropy loss, but it has not yet been successfully applied to speech tasks. So with this in mind, we thought, okay, let's try to see whether we can apply this algorithm to speech. And all the slides that I will present right now is still all very fresh. It's all work in progress. But I want to show you what we did and what we came up with. So how does this like group DRO algorithm work in practice? So basically, the training objective maintains a separate weight for each of the groups you predefine in your training data. And these groups are just uniformly initialized and then updated throughout training. So if you sample a batch, what you do is you compute the average training loss for each group in a batch, and then basically perform an exponential multiplicative update to this group weight vector using the average training loss for each group. Using these updated factor, after performing the updates, you basically normalize the factor again to make it a valid probability distribution. So each of the group weights is basically a value between, or the group weight vector basically sums to 1, with each value being, each group weight being a value between 0 and 1. When you then compute the loss that you use in the gradient descent update for the batch, you sum the group losses that are basically weighted by this group weight that we computed earlier on. So what we saw in the benchmark of ML Superb, and what's also been shown in the literature, is that very well-performing models are actually fine-tuned using the CTC loss, because many self-supervised models, they are just encoder-only models and needs to be fine-tuned for a specific downstream task. And there are some challenges that I will talk about when optimizing the CTC loss using group DRO. And basically, the overall unification of these challenges is that group DRO is restricted to applications where the losses between groups in the training data are comparable. So the first problem that I wanted to highlight is that CTC has this property of scaling with the length of audio samples and also the length of the corresponding transcriptions. And this is problematic, as shown on this slide. So I took data from ML Superb for 6 different languages that all have the same amount of training data, so this 1 hour that I talked about before. And what we can see is that the distribution of utterance length is very different across languages. So this introduces a problem when we want to compare the losses among groups because of this scaling property. The second, and maybe most important thing, is that even though we would be able to come up with some good way of normalizing and take these length differences into account, the group losses might still not be comparable, as audio samples can be from different speakers, from different domains. They may have like different levels of noise. And this may lead to consistently higher or effectively different irreducible loss values for the groups you consider. And this is abstract, but maybe I can illustrate it with an example. So let's say we're training on data from 3 groups. So we have group 1, 2, 3 here. And group 3 has the highest loss here, but it also has the highest irreducible loss because of the properties of the training data. The nature of this DRO algorithm is that because it computes this exponential update, it will try really hard to assign a high weight to this group, effectively trying to hammer down the performance of this group. But because it hits the irreducible loss value early on, the group weights of the other groups will decrease significantly. And what will happen in practice is that this behavior severely leads to undertraining of groups 1 and 2 because their weights become so low. And this worsens the downstream performance of these groups a lot. So actually, this would then lead to not achieving our goal of improving the performance of the worst performing group, as there will be other groups that will now perform even worse than the original worst performing group. So to address these limitations, we present a new algorithm that is based on group DRO, which we named CTC DRO. So to solve these limitations, we present two contributions. So the first thing is that we need duration matched group losses. The second thing that we need is group-based regularization. And I will talk about these items in our updated version of the algorithm. So basically, to deal with the scaling properties of the CTC loss, what we do is we batch the same total duration of audio data for each group instead of like randomly selecting a number of utterances for each group. Then what we do is instead of averaging losses within a batch, we now sum them. And this really prevents some artificially low or very high average for batches with either many short or a few long utterances. And because batches now have the property that they have the same duration, the sum actually ensures that the losses remain comparable across groups. So what we do is we use these more comparable group losses now to compute the updates to the group weights. And we only do these updates after seeing each of the groups because a batch now strictly contains data from a single language, simulating basically batches with all groups being present. The most significant contribution regarding the updates of the group weights is presented here on line 11. So what we do to mitigate this effect of different irreducible loss values, we basically compute softer updates to the group weights using our new way of computing the group losses. So instead of just computing the exponential multiplicative update based on the group loss, which is weighted by a hyperparameter that is a step size, we now perform updates which are inversely proportional to the current group weight and still proportional to the group loss. And what this does in practice, it basically discourages groups from getting very high group weights, which mitigates these issues with the varying irreducibility of the loss across groups. What it also does, it ensures that groups with a lower group weight basically receive a larger update when the losses during training become similar. And effectively, this just helps them catching up during training. And this prevents this like undertraining behavior that I tried to explain on one of the previous slides. The other last thing I wanted to highlight is that we introduced a new hyperparameter alpha here that allows us basically to control the strength of this effect. At the end of the algorithm, what we do is we also multiply the weighted losses by the number of groups, which we have found in our preliminary experiments to improve training stability a lot. So because the losses are weighted by the group weight value, which is a value smaller than 1, we upweight them basically by this multiplication. And this also makes sure that losses are basically in the same ballpark as those models trained without CTC DRO, which makes it easier to not tune hyperparameters for all the different models. So in practice, what we also do is we accumulate gradients across, in our experiments right now, 16 batches before updating the model parameters. So we simulate actually considering batches with multiple groups. Okay, so that's for the algorithm. So what does the experimental setup looks like? So we take the best performing models from the ML Super benchmark, which were MMS and XLSR, and we fine-tune them for the same task. So language identification plus multilingual speech recognition. So we fine tune different models. So we do models with our CTC training objective, with the original group DRO objective, and just with regular CTC fine tuning, which we regard as our baseline models. And the groups in the algorithm basically correspond to the individual languages in the training data set. So for this purpose, what we do is we use the CTC framework that I previously mentioned with a two-layer transformer encoder added on top of the pre-trained models. And in this setting, we update not partial weights, but just all weights during fine-tuning. And we tune the learning rate of the non-DRO baseline models based on the development data and use the same learning rate for our DRO models to enable like a very clear comparison and trying to see most clearly what the contribution of our new training objectives is. So for DRO, we had the step size used to weight the learning rate, and we try two different values that are informed by previous work on group DRO, and we tried three different values for our smoothing parameter alpha, 0.1, 0.5, and 1. So regarding our data sets, we sample 5 different subsets from the ML Superb data sets, consisting of 6 languages each to keep training a bit lightweight. So these languages are sampled at random, with the only constraint that we wanted to have some variation in terms of character error rate there. So we took the best performing configuration of the ML Superb benchmark, looked at the character error rates outputted by the model, and selected 2 languages within each subset that had the were among the 10% worst character error rates, 2 languages which had like the 10% best character error rates, and 2 languages from the part in between. And this sampling approach was applied 5 times. So we have these 5 different subsets with languages that are diverse in terms of their language family and also diverse in terms of the corpus they were from. Cool. So let's look at the results for each of these subsets. So what we see in these tables is the 2 different models that we fine-tuned, so MMS and XLSR. We have the baseline, which is just regular CTC fine-tuning. We have the group DRO training objective and our CTC DRO training objective. So we show the language identification accuracy and the character error rates for each of the individual languages, as well as the character error rate averaged across languages. So what we see, for example, is for MMS is that the baseline indeed shows very large performance differences across languages. And the group DRO algorithm is basically not able to improve the performance of the worst performing language that I highlighted here in yellow. So this is Minnan Chinese. Also in group DRO, as a result of the worsened performance for many of the languages, the average went up. And we see actually that with our adaptation of the algorithm, so the duration matched computation of the group losses and the softer updates to the group weights, we are able to reduce the character error rate of the worst performing language. And actually, this also applies to not only the worst performing one, but also Mandarin, which has which performs very closely in terms of character error rate to Minnan Chinese, which basically leads to a reduced average character error rate as well. And we observe the same trend for XLSR, where we have very high character error rate for Mandarin, which is then substantially reduced with our CTC DRO algorithm. So this seems like artificially high. So I looked into actually the behavior of the algorithm. And what happened is that with this little data of 1 hour, the model makes a lot of mistakes in terms of script differences. So for many of the test utterances of Mandarin, the baseline model actually tried to use a Latin alphabet to generate transcriptions, leading to this extremely high character error rate. And although CTC-DRO is not perfect, definitely not, it does a much better job actually than the baseline model. So moving on to the results from the other subsets, we basically see the same trends. So here we have Cantonese showing that, again, group DRO was not able to improve or reduce the character error rate, but CTC DRO does a slightly better job compared to the baseline. And this effect is even more strong looking at XLSR. And in each of the cases, CTC DRO is actually able to improve the average performance as well for both models compared to the baseline. For the third language subset, we also see that CTC DRO outperforms group DRO. So this is basically the same reasoning that we applied to the previous slide. So baseline exhibiting performance differences between languages that are large. Group DRO makes it a tiny bit better in this case, so it doesn't worsen it. But again, CTC DRO leads to a more stronger effect of reducing the character error rate of the worst performing language, also improving the character error rate on average. So what happened here with group DRO for the MMS model, for example, is that it was able to reduce the performance of the character error rate of the worst performing language, but at a significant cost of worsening the performance on others, which is basically in line with the general intuition that I try to explain when introducing the algorithm. The fourth subset is also in line with this. So yeah, basically we have consistent results across all our 5 subsets. So here again, the DRO algorithm, CTC DRO algorithm is able to, again, reduce the character error rate of the worst performing language and also improves the performance on average for both models. So here for XLSR on Urdu, group DRO does a slightly better job on maybe this language, but CTC DRO has a much lower character error rate on average. So this is these are the results on the last subset. So we see again very strong reductions in character error rate for CTC DRO compared to the baseline. Again, outperforming our group DRO training objective. So to shed a bit of light on what is actually going on with the computation of the group weights, what I did is I plotted the DRO weights over time, over training for each of the languages. And this basically also illustrates and confirms our intuition that group DRO out of the box really leads to weights fluctuating a lot. And also during large portions of training, the DRO weight is basically concentrated on a single language. And while sometimes it concentrates on a language that is actually among the worst performing ones, so here the red line, what also happens is that languages that are basically not at all among the worst performing languages have a very, very high weight. So in green, this is Polish, which was actually among the better performing ones. But it could very well be that the model has the higher loss towards the end of training, and the higher irreducible loss value was basically hit here, causing the model weights to go up. And with CTC DRO, the weights fluctuate a lot less. And what we see is that some languages are definitely massively undertrained because they have a very, very small weight in the group DRO algorithm. And this is basically looking much better with CTC DRO, which causes that like the other languages do not suffer a lot. So here we have a lot of weight on Mandarin, which was the second worst performing language, but also the actual worst performing language receives considerable attention here. So it's the line in blue for Min non-Chinese. And all of the other languages receive some attention as well, mitigating this undertraining effect. So also for another subset, so this is the last subset we looked at, we see basically the same trends with large fluctuating weights. And here Spanish, which was also one of the better performing languages, receiving a lot of attention towards the end of training, really pushing the group weights of the other languages close to zero, which is looking much, much better in the CTC DRO algorithm, where weights are grouped much more tightly, leaving room for the other languages to receive some attention and mitigating this undertraining effect. So one of the last things I wanted to highlight is just showing the contribution of R2 modifications or contributions to the CTC algorithm, CTC DRO algorithm. So the first thing is that we do an ablation study here, where we first remove the duration match group losses procedure, and in the other case, we remove the way of performing softer updates to the group weights. And we see actually that both of them contribute substantially to reducing the character error rate of the worst performing language. And in particular, it seems that the softer updates are very important here, leading that the other groups basically receive some attention during training, and that the character error rate basically gets reduced the most. So to wrap this part up, we find that CTC DRO consistently across the subsets we evaluated reduced the worst language character error rate, and also in most cases improved the character error rate on average. And there are a lot of like very interesting directions for future work that we will consider. So this now considers subsets of 6 languages, which we will scale up in the future. We will also consider more models, different models, perhaps also different downstream models that we can put on top of the self-supervised models. And ideally also look at how we can automatically identify group definitions in our training data, which can maybe even be multidimensional to be even more accurate of how the training data is like naturally distributed. So multidimensional can mean something like combinations of language and speaker's gender or age, at least a like combination of different speaker characteristics. So in this talk, I basically presented 2 contributions where we now have ML Superb 2.0, which provides a way to reliably measure speech recognition model performance. And even though there are like still very much large performance differences between languages, we now have CTC DRO, which can help reduce the performance gap between languages. And I really hope this type of work can be a stepping stone to help improve universal access to modern speech technology. Thank you a lot for listening. I really appreciate it. And of course, also many thanks to all my wonderful collaborators that I listed on the slides. And I think there's hopefully maybe a tiny bit of time to take some questions. And otherwise, feel free to like send me an email or find me on social media. Happy to discuss more of our work.
Thank you for the great talk. Thank you. It was really interesting.
Thank you.
Yeah. So if you guys have questions, you can either write them in the chat or raise your hand to ask them directly. I do have a question.
Sure.
So on slide 65,
65. Okay,
yeah,
let me find it. Yes.
yeah. I was wondering if you could please explain the relationship between the weights and the loss.
Yes. So the nature of or the intuition behind the group DRO algorithm is that basically if the loss is high, you want to assign a high weight to this group. So basically you identify the worst performing language or the worst performing group via the loss. So as
Oh,
long as your group has the highest loss throughout training, you want to keep assigning a high weight in order to make the loss go down faster compared to the other groups, basically. That's some way
okay.
to think about this.
So you don't train all the groups together. You
Well, what you do is you, for example, in the original work, you just sample a batch
Mhm.
containing each of the groups, but you compute the loss for each group individually.
Okay.
So So that's the intuition behind the algorithm, basically trying to isolate the effect of the different groups and then see which group actually performs worse based on the loss. And then the DRO algorithm, by computing these weights, basically tries to improve or reduce the loss by assigning higher weight values to higher losses. And this should
Oh,
ideally lead to like these losses going down and like improving the performance of the worst performing group compared to the others.
okay. And so once you update the weights, do you retrain the models like using all the groups together, or do you just like select
Yeah,
same
so
strategy?
this is basically an iterative process. So you just like you sample a batch containing, in our case, just a group. Then you perform the sequence of updates. Then you go on to the next iteration, sample another batch, and do this like throughout training. And
Oh, okay.
when we update the group weights is after we see all the groups, and then we accumulate gradients across like several batches to simulate like training with basically more than one group at once.
Okay. Okay, interesting. Thank you so much. I think Pune has a question.
Sure.
Yeah, yeah. Thank you. That's really interesting. So I have one question regarding the weights. Have you done any analysis on the similarity of the languages and the weights assigned to them? So what have you done any analysis in that regard? Because the main reason that I ask is like I think it would be interesting to see if you want to add new languages, maybe you could use this similarity score to see what would be the good weight to assign at the beginning.
Yes, I think this is definitely very interesting, and we haven't gone to the part yet where we really like very thoroughly analyze what's going on behind the scenes rather than the intuition of how the weights should behave. But I think definitely like effects of language similarity are so strong when like considering downstream performance, for example, like training with related languages makes a huge deal, even for like similarity between fine-tuning languages versus those that are included during pre-training. So I would bet that these plots would look different if you have like a large degree of similarity versus languages that are more like weakly related. And perhaps there are some takeaways there where we can either leverage these characteristics or, yeah, basically exploit that further to improve performance for on these models. I think that would be very well possible. Yeah,
Oh, interesting. Thank you.
of course.
Well, it-
Oh, I think there are no more questions.
okay, perfect. Um, Thank you again. It was a really interesting talk. I really enjoyed that. And
Thank
thank you
you.
for everyone who is joining. Next week, we will have Piotr Zalasko from NVIDIA. He will be talking about foundational speech model and their efficient training with NVIDIA NeMo. So hope to looking to see all of you next session. Thank you all. Bye.